Hello guys, building muscles can be difficult after passing the newbie's growth period. Besides the significant need of a proper diet, after all, it takes time for the body to recover and synthesize through a number of cycles to reach your desired destination. Some might turn to steroids for quicker muscle growth, but if you want to stay natural and still have a better gains, understanding the body mechanics and adapting it to your training is the way to go. Today we're going to take a look at the major energy production systems, muscle fiber structure, and what you can do to train smarter with all the information. To do this, let's take all the way back to the beginning. First, you have food, then carbohydrates, proteins, fat, vitamins, and minerals. After a series of processes in your digestive system, you have glucose, slowly releasing to your bloodstream. Glucose is one of the few entry tickets that can kickstart the energy production systems that will eventually yield ATP for every cell inside your body. And I mean every cell. Let's pause for a moment and take a look at the ATP function first. ATP, aka adenosine triphosphate, is a stored energy that's often being viewed as the currency of energy of a cell. ATP consists of three parts: adenine base, ribose sugar, and phosphate groups. There are lots of potential energy stored in phosphate groups. They are high energy bonds because electrons in these bonds are in high energy state, ready to be released. It's kind of like a compressed spring. The potential energy can convert it to kinetic energy. When ATP transfers one phosphate group to something else during enzymatic reaction, like hydrolysis for instance, ATP will become ADP, adenosine diphosphate. This transferring or splitting process releases some of that potential energy for any work of chemical reaction, like pumping ions across a membrane or muscle contractions. This is the actual energy that causes metabolism to move. ADP can be phosphorylated, meaning it can be added to one more phosphate group to become ATP again. This reversible method between the two forms is the way nature has discovered to provide energy for cellular processes. We, the human race, and other living organisms are benefiting from it. Now coming back to your bloodstream, when glucose blood level is high, insulin will signal the cells by binding to start breaking down glucose, thus the activation of glycolysis. Insulin and glucagon are the regulators to ensure your sugar blood level is at a delicate balance. Glycolysis happens in the cytoplasm of a cell, yielding a small amount of ATP, a bit of electron carriers, and two pyruvates. There are two pathways for pyruvates to go, with oxygen or without oxygen inside the cell. While the fermentation pathway will turn pyruvate to lactic acid or ethanol and carbon dioxide for ATP, the most yields of energy are in this one, the citric acid cycle and electron transport chain. It is also known as aerobic respiration cycle because the final acceptor will be oxygen. If pyruvates choose this pathway, the citric acid cycle, known as TCA, will take place in the mitochondrial matrix. A pyruvate will get converted to acetyl-CoA before entering the cycle. The forever loop of TCA will facilitate energy extraction to squeeze every bit of whatever the acetyl-CoA has and place the electrons to electron carriers for their final destination. Meanwhile, CO2 is produced, and it is the same gas that eventually exhales out of your body. Now, the electron transport chain is the most useful cycle of generating ATP for your cell because it leverages a bunch of photons inside the mitochondria. Several large complexes work as cannons and shoot photons to the other side to create a pool of photon gradients, while the energy of electrons are getting low during changing hands. Eventually, electrons will meet their final acceptor, oxygen, and form water that will be spent elsewhere. Because of its high concentration of photons here, these photons are not happy about it due to the electrochemical potential differences between the membrane and desperate to go back in. At this point, we can see that this particular mitochondrion had just created a lot of potential energy at the intermembrane. This will be great for energy harvesting, isn't it? But wait, we need a door to let them back in. You see this marvelous enzyme here? He's like the bouncer at every photon shootout event inside the human mitochondria, being a gateway allowing the photons to come back in. It's designed like a turbine in a hydroelectric power plant. It's called ATP synthase. When all of the photons rush to this gate, they drive the rotation inside the synthase, just like how water drives the turbine's rotation, causing the inorganic phosphate to bind to ADP. As this happens, a phosphate group is added to the ADP molecule, forming ATP. That's the ATP ready for your cell. Now the cycles are good, from glycolysis to TCA to ETC. Together, they generate many ATP after each cycle ends for your cell's energy. But running a cycle takes time. Wouldn't it be more efficient if we have something available on site, at least for the first 30 seconds or so? Here's where the phosphation system comes in. The phosphation system is no more than a portable energy bank for your cells to get energy from immediately. So this system is simple, and it is not an energy production system. Human body can naturally synthesize creatine. It is a chemical compound. The main job of creatine is to take up a phosphate group from the ATP to become phosphocreatine. So the pathways of glycolysis and TCA cycle can continue on their cycles, additionally providing immediate energy for whatever you need. At rest, about 2/3 of the creatine capacity in skeletal muscles is available in the form of phosphocreatine by the action of the enzyme creatine kinase. During intense, short-duration exercises, muscles rely heavily on phosphocreatine to provide instant energy. The phosphate group from the phosphocreatine transfers back to ADP to make ATP, and this ATP is used for myosin muscle contraction. This reversible process of creatine and phosphocreatine ensures the continuous energy supply available to the muscles. Keep in mind that however much creatine you digest, according to Le Chatelier's principle, that means you'll also end up with lots of phosphocreatines in your system because the body will always want to be at equilibrium. Depending on your diet and genetics, you might not have a reaction to creatine supplement. If you do improve because of creatine, it is because your body is able to saturate your muscles with creatine. The phosphation system is important because this system and glycolysis will always be utilized first whenever you start using the muscles. But the demand for it will subside quickly, and the TCA cycle will take over to continue providing ATP for those muscles when the intensity isn't high enough.